So what's up guys, this is the Round Bottom Flask and welcome to the part 2 of our video lecture series for Chemical Equilibrium. For this video, I will be discussing the other aspects of the equilibrium constants. Now what we have shown here, especially in the part 1 of our video lecture series, the link is embedded in the description below this video, is that the equilibrium constant is expressed in terms of the molar concentration of your reactants and products involved in the reversible reaction. Now, in the gas phase, there's also another way of expressing the equilibrium constant. Now, this is only applicable if all of your reactants and products are in the gas phase. So we can express it in terms of the partial pressure of both reactants and products. So let's have this hypothetical reversible reaction here. Now, the equilibrium constant in terms of partial pressure, denoted as Kp, is defined by this expression. Now, this expression of your Kp is not that different with your Kc, because it's still product over reactant, and the partial pressures of your products and your reactants are raised to the power of their respective stoichiometric coefficients in their balanced reaction. But again, the difference is that instead of using their concentration in moles per liter, we're using their partial pressure in terms of atmospheres. Now, we can actually establish a relationship between Kp and Kc if we assume that the gases in this reversible reaction behave ideally. So if they are ideal gases, they will follow the ideal gas equation, which I'm pretty sure we are very familiar with. Now, from this ideal gas equation, we can actually establish a relationship between the partial pressure and the concentration of your component in the reversible reaction. So let's take, for example, we'll go back in the previous slide. Let's take, for example, our component A here. We'll use it as our some sort of a model. So let's take our component A. So let's apply the ideal gas equation in our component A. So it would look like this, wherein PA is the partial pressure of A, and obviously the V is the volume of the reaction vessel, wherein the reversible reaction in gaseous phase occurs. So vessel, and N is obviously the number of moles of A. So R is obviously the universal gas constant, and T is the temperature in Kelvin. Now, what we do here is, I'll erase this one. Now let's divide both sides of the equation by V. So this will cancel out, and that will give you, I will delete this one because it will show in the next the next transition would look like this, okay? And we know that N is the number of moles and V is the volume of the reaction mixture. So if we express V in terms of liters, which is usually done when we're dealing with gases, so therefore moles per liter, and we know that is the molar concentration of your component A. So we substitute this expression to our ideal gas equation here. So therefore, the pressure, the partial pressure of A is equal to its molar concentration multiplied by the ideal gas constant and the temperature of the reaction. So we have used our component A as our some sort of model. Now we can apply this to the components to the other components in this hypothetical reaction occurring in the gas phase. Okay, so we apply it and we substitute it all over here to each of their components in the Kp expression, and it would look like this. So we apply our exponential laws wherein m times mn raised to the power of a, the exponent a will be distributed on both terms, so that is equal to ma and a. Okay, we will do the same to each of these expressions for each component in the reversible reaction. So it would basically look like this. Now this is kind of a shortcut, because after I distributed the exponents, I factored out the common factor, which is your RT. Now we can factor out RT since they are a common denominator here, right? Now we know that a raised to the m and times a raised to the n is equal to a raised to the power of m plus n. So since we have a common denominator here, we have a common expression here, which is RT. The only difference is their exponent. So we will apply that same same exponential law to here to some sort of simplify it. So it would look like this. Now you will also do this in the denominator. So after that, we will apply our exponential law, which is m raised to the power of n divided by m raised to the power of r, and that is equal to m is equals to n minus r. Now remember that they have the same term but raised to different values, so therefore this values will subtract each other in the exponent. So we will use that logarithmic law to further simplify this previous expression here. So what it would look like will be, I'll delete this one. It would now look like this. So CD is equals to a plus b. So originally it is from, I will just write it down here, RT C plus D all over RT raised to the power of a plus b. So what will happen is we will apply the exponential laws, and it would look like this. So RT C plus D minus a plus b, open close parentheses. Now if we remove the parentheses here, this a will become positive and b will become negatives. Thus it would look like this. And we know that this term, this expression here, is our equilibrium constant in terms of concentration. Thus, we can now establish a relationship between the Kp and Kc. So the final equation, or our working equation, would be Kp is equal to Kc multiplied by Rn raised to the power of Rt raised to the power of delta n, wherein n is equal to the coefficients of the products minus the coefficients of reactants in their balanced reaction. So let's try answering some exercises that we have here. So calculate the Kc for each reaction at 298 Kelvin. So let's have letter A. So what you have to do first is we need to determine whether the reaction is balanced or not. So let's have letter A here. So iodine gas will dissociate reversibly to form your gaseous iodine atom. So obviously this reaction is not balanced. Therefore, we balance the reaction since the only element present here is iodine. So we have two iodine atoms here, but only one iodine atom here. So we will multiply this by 2 to make the equation balanced. And as you can see, the equation is already balanced. So we already have the value for Kp. Therefore, our Kp is equals to Kc multiplied by RT raised to the power of delta N. And we divide both sides of the equation by RT raised to the power of delta N. So that will cancel out. Therefore, Kc is equal to Kp divided by RT raised to the power of delta N. Then we substitute the reaction, or rather we substitute the values. So Kp is equal to, it's already established here, 6.26 times 10 to the negative 22 multiplied by 0.08206 liter atmosphere per mole Kelvin multiplied by the temperature, which is 298 Kelvin. And remember that these are all raised to the power of delta N. So our delta N is product minus reactant. So coefficient of the product minus reactant, so 2 minus 1, that is equal to 1. So the equation is equal to 6.26 times 10 to the negative 22 multiplied by 0.08206 times 298. And that is equal to and that is equal to 2.560 times 10 to the negative 23. So that will be our Kc for letter A. So let's have another example, which is our letter B. I will erase this one. So for letter B, we have we have this one here. So let's have our balance equation here. So let's have this one. Let's balance our equation first. So we have our only elements, carbon, hydrogen, and oxygen. So carbon, hydrogen, and oxygen. So in the reactant side, we have one carbon atom and we have 4 in this molecule, in this compound here, plus 2 from the water, and 1 oxygen molecule here. So that we will have a total of 4 plus 2, 6 hydrogen atoms on the reactant side. On the product side, we have 1, which is coming from the carbon monoxide, 2 from the hydrogen gas, and 1 coming from the monoxide, a carbon monoxide, that is for oxygen. So this is pretty straightforward. We multiply the hydrogen gas here in the product side by 3, and we will have 6 hydrogen atoms here, which balances the number of hydrogens. Now, the number of carbon and oxygen on both sides are already balanced, so we just need to add a coefficient of 3 here on the hydrogen gas on the product side. Next is we calculate now the Kc for letter B. So we have already established in our previous problem in letter A that Kc is equals to Kp divided by RT raised to the power of delta n. So let's establish first what is our delta n. Our delta n is the coefficients of the products minus the coefficients of the reactants in the balance equation. So on the products, we have 3 for the hydrogen gas plus 1 for the carbon monoxide minus 1 for the methane gas and 1 for the water molecule. So that is 3 plus 1, that is 4 minus 1 minus 1. So that is equal to 2. So our delta n is equal to 2. Therefore, our Kc is equals to, we substitute now our values, which is 7.7 times 10 to the 24th divided by 0.08206 multiplied by our temperature, which is 298 Kelvin. Then we raise it to the power of 2, and that is equal to 1.288 rounded off to 4 significant figures times 10 to the 22. Now remember, just like your Kc, your Kp does not also have a unit. Let's have another example here. The equilibrium, the reaction shown below, reaction is shown here on the slide, is established at 500 Kelvin. An equilibrium mixture of the 3 gases in a 5-liter vessel has partial pressures of 0.095 atmospheres, 0.171 atmospheres, and 0.28 atmospheres for a nitrous oxide, or is it nitrous oxide or nitrogen monoxide, chlorine gas, and NOCl respectively. Calculate the Kp and the Kc for the said reaction. So before, as I've told in my previous lecture videos, that when dealing with problem-solving questions just like this one, we need to establish first the given. So our given, this helps us identify which of the following information will be necessary for our problem solving. So given is we already have the reaction. So I'm just gonna write the reaction for emphasis. Plus Cl2 then we have the partial pressure of your nitrogen monoxide, which is 0.095 atm. The partial pressure of chlorine gas, which is equal to 0.28 atmospheres. And the partial pressure for NOCl, which is equal to... So for chlorine, it's actually 0.171, 0.171, atmospheres, and for NOCl, it is 0.28 atmospheres. Then we need the temperature at 500 Kelvin, which is a temperature. Now, do we need the volume of the vessel? In this case, no, because we can actually obtain our Kc from the Kp. If we're doing Kc without these partial pressures, we will actually need the volume of the vessel. Since we already have the partial pressures of the gases involved in the equilibrium, we don't need the volume of the reaction vessel because we can obtain the Kc directly now from Kp. So what is required is the equilibrium constants in terms of your pressure, of partial pressure or pressure, and in terms of your concentration. So the first, based on the information given, the one that we can directly solve will be the Kp. So we will do that first. So we'll establish first the expression for our Kp. So again, it's product over reactant raised to their respective stoichiometric coefficients in the balance reaction. So since our reactant is our NOCl, or our product is our NOCl, so it will be the partial pressure of your NOCl raised to the power of its coefficient, which is 2 all over a partial pressure of your nitrogen monoxide raised to the power of 2 multiplied by the partial pressure of your chlorine gas. This is just simply direct substitution, so this is equal to 0.28 squared multiplied by 0.095 squared times 0.171. And that is equal to, rounded off to 4 significant figures, 50.80. So again, Kp is unitless. Then we have shown that in our previous slides, that Kc is equal to Kp divided by RT raised to the power of delta n. So let's establish first how much is our delta n. Now our delta n is the coefficients of the product minus that of the reactant. So our product is only NOCl with a coefficient of 2, so that is 2 minus the 2 from the nitrogen monoxide and the 1 from your chlorine gas, and that is equal to -1. So therefore, I'll just put it here. Therefore, Kc is equals to Kp all over RT raised to the power of -1. Now we know that any value raised to a negative number, raised to the power of a negative number, is equal to the reciprocal of that value raised to the power of the positive component. So that would mean that RT raised to the power of -1 is equals to 1 over RT raised to the power of the positive value for the exponent, which is equal to -1, positive 1 rather. So that is equal to 1 over RT. So we will substitute that, we will apply that here. So therefore Kc is equals to Kp divided by 1 over RT. Since this will be transferred to the numerator, so that means our working equation will be Kc is equals to Kp times RT. Then we substitute the values, which is equal to 50.8. We use the universal gas constant, which is 0.08206, and the temperature at Kelvin, which is 500 Kelvin, and that is equal to 4 significant figures, that is 2084. So these will be your final answers. Your KP is 50.80 and your KC is 2084. Now, we have shown so far in both the part 1 and on the previous slide, equilibrium, or rather reversible reactions, wherein all of the components are on the same phase. However, what if our equilibrium or reversible reaction occurs on different phases? So what does that mean? That means either one of the products or the reactants are on the different phase as of the rest of the components in the chemical equilibrium. So how do we address that? So those kind of chemical equilibria are what we call as heterogeneous equilibria. Now, experimental data has shown that liquid and solid components does not affect the equilibrium. So for example, let's have the dissolution or the reversible dissolution of your lead 2 chloride in water. So your lead 2 chloride, when dissolved in water, will dissociate into its individual ions. Now, since this is a solid, this reversible dissociation can be expressed by this one here. So this will not change, okay? This one will only are the ones involved in the equilibrium constant expression for this reversible dissociation of lead 2 chloride. So why does the solid and liquid components are not included rather in the equilibrium constant expression? So let's have this example here. Let's have our carbon. Let's have the the combination reaction of carbon monoxide to form your carbon dioxide and your solid carbon as a byproduct. Now let's say we already have what they call this. Let's say we already have an equilibrium chamber wherein the carbon dioxide and carbon monoxide are already at their equilibrium concentrations. So let's say this one has this vessel here has fewer solid carbon in comparison to this vessel on the right. So what happened here? So ideally, there should be a difference in the equilibrium concentrations of both carbon dioxide and carbon monoxide, since the vessel of the right has more solid carbon. Okay. However, it was observed that regardless of the amount of solid carbon present in the equilibrium mixture, the equilibrium concentrations of the gaseous components in this reaction does not change. Therefore, this is because that the concentration of solids and liquids do not change after the equilibrium is established. It's because they are on a different phase with comparison in comparison to the other components of the mixture. So for example, let's say this has a volume of V1 and this has a volume of V2. Now, the volumes of the carbon solid carbon here is entirely different, is independent on the volume of the reaction chamber. It does not occupy the same space it does not occupy the whole reaction chamber, unlike when it is a gas that it distributes itself throughout the reaction chamber. Solids and liquids are not able to do that because they are condensed in, they are what we call as condensed phases in nature, and they have a defined volume. So this is not applicable here, and thus they will not induce any change in the equilibrium once that chemical equilibrium is established. So let's have an example here. So ammonium carbonate with this chemical formula decomposes to ammonia gas and carbon dioxide in this reversible reaction here. Now, starting with only the solid, it is found that at 40 degrees centigrade, the total gas pressure, which includes that of the ammonia gas and the carbon dioxide gas, is 0.363 atmospheres. Calculate the equilibrium constant in terms of partial pressure, which is Kp. So again, we'll write our given. We'll establish, we'll just write our reaction for emphasis. So ammonium carbonate will decompose to form your gaseous ammonia and your carbon dioxide gas. So our equilibrium constant expression in terms, or rather, sorry, before that, we write what is required, which is our Kp. I forgot to write down the total pressure, which is also given, so that is equal to 0.363 atmospheres, and the temperature, which is equal to 40 degrees centigrade. And since the temperature should be in Kelvin when we're calculating Kp, and so we just add 200, a value of 273.15 to convert it to Kp. Or to convert it to Kelvin, and that is equal to 40 plus, that is equal to 277.15 Kelvin. So we have the required, which is our Kp. So to solve this, we need to establish our Kp expression first. So our Kp expression is, since the ammonium carbonate is solid, it is not involved in the Kp expression. What is involved is only the ammonia gas and the carbon dioxide gas. So Kp is equal to the partial pressure of ammonia raised to the power of 2 squared, because the ammonia has a coefficient of 2 multiplied by partial pressure of the carbon dioxide. What we're just given here is the partial pressure of, or rather the total pressure of, in the vessel at equilibrium. So we know that since the components present only there are your ammonia and your carbon dioxide, so therefore the total pressure is equals to the partial pressure of ammonia plus the partial pressure of carbon dioxide. Now, we have seen in the ideal gas equation that the partial pressure is equals to the number of moles divided by the volume multiplied by RT. So we will use that same model for the partial pressure of ammonia and carbon dioxide. So the partial pressure of ammonia is equal to is equal to the number of moles of ammonia multiplied by gas constant and the temperature divided by the volume of the vessel. Same goes for the partial pressure of your carbon dioxide. Now, we have seen in this the balanced stoichiometric, the balanced chemical reaction that 1 mole, that when the when 1 mole of ammonium carbamate decomposes, it produces 2 mole of your ammonia and 1 mole of your carbon dioxide. So based on the balanced reaction, that means that for every 1 mole of your carbon dioxide present, that is equivalent to 2 moles of your ammonia that was also produced in the decomposition reaction. So we will use this relationship to establish our relationship between the NNH3 and the NCO2. So therefore, NCO2 is equals to 2 mole of your ammonia. So how does this help? So that means we can actually express one partial pressure in terms of the partial pressure of the other. So let's try substituting the NCO2, the expression for the number of moles of carbon dioxide to here. So therefore, the partial pressure of CO2 is equals to 2 mole, number of mole times number of mole of ammonia multiplied by gas constant and the temperature of the reaction divided by the volume of the vessel. So we know, and now we know that this expression is the partial expression for the partial pressure of your ammonia. Therefore, we substitute it in this equation to establish a relationship between the partial pressures of the two components. Therefore, the partial pressure of your carbon dioxide is equals to the partial pressure of ammonia multiplied by 2. And we will use this relationship to get in our equation for the partial pressure to get our total pressure to get the partial pressure of ammonia. So that means that partial pressure, total pressure is equals to, we substitute this expression to here. So partial pressure of ammonia plus 2 times the partial pressure of ammonia, and that is equals to P to 3, or 1 plus 2, that is 3, so that is 3 times the partial pressure of ammonia. And since the total pressure is given, therefore, the partial pressure of ammonia, we divide both sides of the equation by 3 is equals to the total pressure divided by 3, and that is equals to 0.363 divided by 3, and that is equals to 0.121 atmospheres. And we can actually use this to get, we can substitute this expression to here to get the partial pressure of your carbon dioxide. So the partial pressure of your carbon dioxide is 2 multiplied by 0.121 atmospheres, and that is equal to 0.242 atmospheres. So we can now get the Kp since we already have the partial pressure for the components. So Kp is equals to 0.121 squared multiplied by 0.242. And that is equal to rounded off to four significant figures, 3.543 times 10 to the negative 3. So that is our Kp. So let's have our last example here for the reaction. For the hypothetical reaction as shown here, a reaction vessel initially contains only A at the pressure of 1.32 atmospheres. At equilibrium, the partial pressure of A is already down at 0.25 atmospheres. Calculate the value of Kp. So we already have our answer here. We just need to know how to arrive from this answer. So again, we write our given, which is, I will write the reaction for emphasis. Then our initial partial pressure for A, that is equal to 1.32. So let's say our initial pressure for A is denoted as 1, so that is equal to 1.32 atmospheres, and the equilibrium pressure of A is denoted as 2. So that is equal to 0.25 atmospheres. So what is required in this case is the Kp. So let's establish the solution. Now again, we'll establish first our Kp expression. So Kp is again product over reactant. So since our product is B, therefore its Kp is a partial pressure of B raised to its coefficient, which is 2, all over the partial pressure of A, and this is at equilibrium. Now we already have the equilibrium partial pressure of A, which is our 0.25 atmospheres, so this is our PA2, but we don't have the the partial pressure of B at equilibrium. So we will actually use the difference between the initial and equilibrium pressure of A in order to get the partial pressure of B at equilibrium. So let's establish first our ideal gas equation for the gases A, both initially at and at equilibrium. So PA1 V equals to NA initially over RT. Same goes with at equilibrium. Now we know that the number of moles of B produced in the reaction is equal to or can be related to the number of moles of A lost during the establishment of the equilibrium. So it is actually directly proportional to the number of moles of A initially minus the number of moles of A at equilibrium. Now, this is just yet a relationship instead of an equation, because we need to consider these stoichiometric coefficients. Now remember that the number of moles of A initially minus the number of moles of A at equilibrium is the number of moles of A converted to B. So how do we get the number of moles of B formed? So that is equal. So we need to convert this moles of A to moles of B. So that means, so let's say we have Na moles of A. Okay, we use the coefficients in the stoichiometric, in the balance reaction, to convert this to B. So we know that based on the balance reaction, that 1 mole of A can be transformed into 2 moles of B. So it would look like this. Therefore, NB, number of moles of B, is equals to 2 multiplied by the number of moles of A converted. And we can substitute this to, and we can substitute this expression to here. Therefore, the number of moles of B is equals to 2 multiplied by the number of moles of A initially minus the number of moles of A at equilibrium. Now, where do we get these values here? So these values are still unknown. So how do we convert this into an expression wherein we already have a known value? So we use the ideal gas equation. Remember that based on the ideal gas equation, we can actually manipulate this so that only the number of moles is on one side of the equation. So Na, we'll use the number of moles of A initially as our some sort of model. So that is equal to Pa raised to the power of 1 over V divided by RT. So we will use this expression to substitute it to this expression of the number of moles of B at equilibrium. So that is equal to 2 multiplied by Pa 1 V over RT minus, so this is actually small letter p, is 2 V over RT. So we can actually factor out V over RT to make it look like this. So 2 multiplied by Pa1 minus Pa2. This is supposed to be small letter, sorry. V all over RT. Okay, next that we do is we transfer V over RT on the other side of the equation so that only the knowns are on one side and only the unknowns are on the other side. So your working equation will be, I'm running out of space. Can I just delete this one? I don't know. I'm running out of space. I'll just delete this one here. So that would be equal to so that would be equal to 2 raised to the power of Pa1 minus Pa2 equals 2 NB RT over V. And we have already seen this expression on our previous slides, and this will be this is actually the expression for the partial pressure of B at equilibrium. Therefore, the partial pressure of B at equilibrium is equal to 2 multiplied by the difference in the initial and equilibrium partial pressures of A. So we substitute we substitute the value, so that is equals to 2 multiplied by 1.32 minus 0.25. So that is equal to 2.14 atmospheres. Now we can solve for our Kp by substituting our values. So Kp is equals to 2.14 squared divided by 0.25, which is the partial pressure of A at equilibrium, and that is equal to, rounded off to 4 significant figures, 18.32, which is the same with our given answer here. So this ends my video for the part 2 of video lecture series for chemical equilibrium. If you have any questions or if you have any suggestions on what chemistry topic should I do a lecture on next, please feel free to drop your suggestions and your questions in the comment section below. And if you like this video, please don't forget to click the like button, and please subscribe to my YouTube channel for more chemistry related lectures. Once again, this is the Round Bottom Flask signing off. See you guys